personal finance practice problem using OneNote. Excel functions, present value, future value, and number of period Excel functions problem number 3. Let's talk finance, and this time it's personal finance. Here we are in OneNote. If you have access to OneNote, would like to follow along, you're not required to, but if would like to, we're in the icon on the left-hand side. We're in the Practice Problems tab down in the 1120 Excel Functions, Present Value, Future Value, and Number of Periods Excel Functions Problem Number 3 tab. Also note, when using OneNote, take a look at the immersive reader. Many of our presentations will be down in the text area as well with the same name, same number, but with transcripts that can be translated into multiple different languages and either listened to or read in them. Closing the icon, we got our information up top, calculations on down below. We're looking at the present value, future value types of calculations. We're going to look at them in the format of Excel functions here, not in Excel at this point in time, but reviewing them and comparing the Excel function way of calculation to other types of calculation methods. We do work this problem in Excel, however, as well. So if you want to take a look at it in there too, you can. So our information up top, we have the yearly earnings percent in a savings account. It's going to be 18%. So we are assuming then that there's a yearly increase of 18% in our investment. Obviously, that's quite high for a savings account, at least at this point in time. But you can have similar kind of increases in any kind of investment account that we can think about going up, including a home, including land, including stocks, bonds, and so on. And we want to just basically have a different rate than we have seen in our prior problems, a higher rate at the 18%. So our question then is going to be, how long will it take for the account to double, which we looked at in prior presentations, and you don't have to have seen the prior presentations to work through this presentation, which will focus on the method of Excel functions. But we want to see how they're all kind of tied together, or how they get to the same end result, but using different methods so that you can pick the best method for what you are working in, and so that you can basically recognize what other people are doing if they're using some other method than what you would select. So we first have that rule of 72. So the rule of 72 doesn't even need a beginning investment amount. It's just basically 72 divided by the rate in the number format 18. That gave us 4 years. So 4 years we expect to double, which we can do without even having an first initial investment account. Then we assumed the investment account amount of $3,000. So that would mean, based on the rule of 72, that we would think it would double to $6,000 in approximately 4 years if we had the rate of interest annually at 18%. We then did a similar calculation, but having a running balance type of calculation, showing the actual increase in the interest on a period-by-period basis and the increase in the investment. Great tool to have no matter what method we are using, even the Excel functions, which are quite efficient and probably the best method when you are in practice oftentimes. Still useful to also use Excel to get this running balance table so that you can see what the actual impact is with regards to interest as it compounds. We can see here once again between year 4 and 5, we've cleared the doubling of the 3,000 to 6,000. So around 4 years, once again, that 4 years from the rule of 72 being an approximation. Now we're going to do a similar kind of thing, but this time with the function. So we're going to be considering what Excel functions would be doing. Now note, with this particular problem, we're not actually looking for the end result of the future value or the present value. Those two functions you'll think about. If you had a present value kind of function, the idea would be that you have some amount in the future that you're trying to discount back to the present period. That would be the idea of it. So you're trying to get to the end result, which would be the present value. If you're looking at the future value, you're starting typically with a present value function format, and you're trying to see what would happen if you had a rate of growth to some future point in time. So what we're looking at here in this problem isn't really the end result of present or future value. Those two things are known. We know the present value to be 3,000. We know the future value to be twice that because we want to double it, or 6,000. And what we're looking for is the number of time, whether we're going from start to the end, present to future, or future discounting back to the present. What's the interval of time in between? And for that, we could use a different function, which could be called the number of periods function. although that function is less commonly known oftentimes as opposed to the present and future value. In other words, when you first start looking at functions for present and future value kind of calculations, the first two you start with is, of course, present and future value. And you can use those functions in this type of scenario to back into the unknown, which is the number of periods, in a similar way as you can do mathematically. In other words, if you know all the arguments of the function, including what the end result of the function can be, then you can kind of use that algebraic concept of backing into the one unknown. You can't do it by reworking the function yourself, although you can look for another function in Excel, which we'll take a look at, which would be, basically Excel reworking the function. But if you're using this function, you can't rework it, but you can use goal-seek to kind of basically back into or figure out the unknown component. So we'll work this same answer. We'll get to this 4.19 using these three functions here and going through them in three different ways. So let's start off with the future value and see what that would look like within an Excel function. So if we were to plug this into an Excel worksheet, you could use a dialog box to do it, but I think it's easier or better to get an idea of what the actual function looks like if you were to double click on the cell or just type it in there with a good old equal sign. So it would be something like this. We're going to note what's going to happen here. We're going to start at the present, and we're trying to see where we're going to be at the end. At the present, we know we're at the 3,000, and then the future value would typically give us the end result, which we already know needs to be 6,000. And what we're trying to do is back into this number of period function, which actually in the middle of the function, which we're going to basically use goal-seek in order to do. So if I type in this function, then we would say equals negative. The reason I have a negative here is because if you do not have a negative in the entire function, it will come out to a negative number. And so to make it a positive number, you could either put a negative in front of the F, which is probably not the most proper way to do it, but I think it's an easy way to do it. Or more properly, you could put the negative in front of the present value in here as well. And then I'm going to say future value, brackets. That'll give you your argument down here, and this little argument will be separated by the commas that you can then enter in. So the rate then is going to be 18%. You could type in 0.18, or you can point to the cell with 18 in it, that being the better practice because then you're pulling the data from the data input components. Comma, that'll take you to the next argument, which is the number of periods. That's the unknown. That's what we do not know. So what we would do then here is possibly make up another cell down here that I could pick up and put some number in it, typically not leaving it blank, typically not having a 0 in it because those can just distort the function in general, but guessing some number like 10 at the starting point, noting that that cell is the one that we're then going to change to get the end result to see what we need it to be by asking Excel to, in essence, just do that with brute force. Find the number that it needs to be without reworking the function, but just trial and error using a computer to do it. So then we're going to say comma, and then another comma because we don't have a payment component, the payment component being related to an annuity calculation. This is not an annuity calculation. And then we've got the present value then being the 3,000. That's our starting point. Now, if we were to run this function and we didn't know, or we entered down here in this cell for the number of periods, something other than the answer of 4.19, then we would get a result here that would be something other than 6,000. And we'd basically then need to fix it. And we'd say, okay, how can we adjust that? We can adjust this cell because this cell is tied to this formula. And we can just adjust this cell until we get the future value to be what it needs to be. That, in essence, is how we can kind of use the algebraic concept of having one unknown, solving for that one unknown, but not reworking the function, rather using trial and error. We cannot do that by hand, but we can actually ask Excel to do that with a function called goal-seek, saying, hey, please, Excel, would you change this cell to whatever it needs to be, which happens to be 4.19, about 4.19 years, in order to get the end result in here to what we need to know it should be, 6,000, which is the future value, double the investment amount. So we could do the same thing with the present value, and this will highlight kind of how these two formats are related. So in the present value, this function of the present value, we know what the present value is already. It's 3,000. and we're going to use within the function the future value, 6,000, which we already know, to basically get to the end result to be what we think it should be, 3,000. The unknown component then, once again, is the number of periods or the distance, the time frame between the two. So we can start in this format, basically starting at the future value, the end of the function getting us back to the present value, looking something like this. Equals negative. Once again, the reason it's a negative is because if you do not have a negative at all, it will result in a negative value at the end. So you could put a negative here, or you could put it possibly more properly in front of the B7 to fix that. And then we have the present value of the rate. The rate you could type in there at 0.18, but we're going to pull it from our data set up top because that's just better practice. And then comma, number of periods, that's the unknown. So what we're going to do is set up our other cell down here, put something in it, not leaving it blank or 0 because that can distort this function in general, just putting like 10 in there or something like that, noting that we will then go back there and change it using the goal seek, using the trial and error method. Then we're going to say comma, comma, because there's no payment. Payments are for an annuity function. This is not an annuity function, therefore no comma. And then we have, no payment and 2 commas. And then the future value is going to be the 6,000 because it's twice the 3,000. And we could type in 6,000, but we would rather make it 3,000 times 2, drawing our data from our data set once again. Now, if we were to get the result of this function with something other than the answer in here, 4.19, the result would be something other than 3,000. We know the end result needs to be 3,000. Therefore, we can then adjust this cell, since it's connected to this function, to whatever it needs to be. We could lower it from 10 to 9 to 8 and so on, and or ask Excel to do that with goal seek. Excel then doing a trial and error method to solve for the unknown, that unknown being the number of periods. Once again, getting to that 4.19, 4 years and 0.19 to get the 3,000 to double. That's the time frame between the present and future value. So then we can get there more directly. So the other way we could see this is we could say, okay, well, if this is the unknown, I know this present value, and I only have this one unknown. Is there a function for that NPER point? And can't I just use that? We could. We can look for that function. Note that this function can be a little bit tricky though, because when you do that, you're probably going to a function you're less familiar with. So it might still be worthwhile to use this method up top to get an idea of what you think is going to happen and then use this function. So for example, this function needs a negative sign in it, which you might not be as familiar with. And if you do not do that properly, it'll give you a wrong answer. And so it would be nice that if you can then test it out with something that you intuitively understand so that you could get an idea and a feel for any new function you'll be working with. And that's common with many functions you might be using in Excel. So this one, we're going to say equals the NPER brackets and then the rate. Once again, 18%, which you could type in there as 0.18, or you could find the cell for it, which is the more proper way to do it. And then we've got 2 commas because there's no payment, because this is not an annuity calculation. And then we've got the present value. The present value, we have a negative in it. That's where we have to put the negative here, because I don't think it'll work if you put it in front of the N like we did before. So you kind of have to put it in the actual function here to get the thing to calculate. So if you do not get a proper number, then try putting the negative in the payment section and see if that will adjust or fix your problem. And then we've got a comma, and that's the present value, comma, future value, which would be twice the 3,000 or 6,000, which you could hard code or type in there, but it's better to basically point to the cell times 2 so that you can double it in that format. And that once again will get you to the 4.19. So note that these Excel functions are probably the thing that you would use most in practice. But you'd still probably want this running balance table. I highly recommend getting used to these running balance tables as well, because that gives you a better idea of what's actually happening. But if you're in a test situation or in a school situation, then the mathematical formula and the tables will often be something that you will be tested on, and just realize that they will kind of force you to use whatever they want to use. It's almost like a power game, right? They could do that by basically using rounding and stuff, right? So they could say, we want you to use the tables, and take your calculator away, and they can kind of make you use the tables by approximating the answer due to rounding. And if you don't get the correct rounded number, even though that rounding is not significant for really oftentimes decision-making processes, it can distinguish the answer so they can tell what method you used so that you make sure you followed the directions and used the method that they told you that you should use. So we'll go to the tables next time, and maybe not next time, we'll go to the actual mathematical formulas and the tables in future presentations.